Where have we been before we got here? Well, for instance, the State Institute for Highway Safety buys new vehicles each year and crashes them into a barrier for fun. I mean, not for fun. To figure out how different vehicles protect drivers in a frontal offset crash. That's important, isn't it? Yeah, we kind of want to know which cars are safer than others, right? Okay. In this test, 40% of the total width of the vehicle strikes the barrier on the driver's side. The force and impacts that occur during the crash test are measured by equipping dummies with special instruments and placing them in the car. The crash test results include data on head, chest, and leg injuries. For a low crash test number, the injury potential is low. If the high test number is high, then the potential injury is high. Using the techniques from Chapter 8, we can determine whether the mean chest injury potential is the same for pickups and minivans. Remember doing stuff like that? Okay, so here's the table right here that shows some sample statistics. For the mean of chest injury, the p-value for the hypothesis is about 0.7575. At a 5%, what's this called again? Do you remember? What does that stand for? Level of significance, right? Okay. You fail to reject the null hypothesis. So if you do not have enough evidence to conclude that there is a significant difference in the means of the chest injury potential in the frontal offset crash at 40 miles per hour for minivans and pickups. Okay. That's where we've been. We've done problems like that before, right? Well, where are we going? Well, in this chapter, we're going to learn that we can answer a question about, like, is there evidence of a difference for chest injury potentials among minivans, pickups, and midsize SUVs in a frontal offset crash at 40 miles per hour? We focus on one or the other. Now we're able to look at 3 or more. Okay? So we're going to figure out we can answer that question by testing the hypothesis that 3 means are equal. For the means of chest injury, the p-value of a hypothesis, for the hypothesis, that they're all equal is about 0.0088. So at 5% levels of significance, we can reject the null hypothesis. Okay, we're going to figure out how to do all that. So we can conclude that the 3 types of vehicles tested, at least one of the means is different, right? Because if we're rejecting the claim, it doesn't mean that they're all not equal, but it means that at least one of them is not. Does that make sense? Okay, so Chapter 10.1 deals with the chi-squared goodness of fit test. Okay, so the main example that we're going to talk about talks about a tax preparation company. So I'm going to go ahead and talk to you about that a little bit, okay? A tax preparation company wants to determine the proportions of people who use different methods to prepare their taxes. To determine these proportions, the company can perform a multinomial experiment. A multinomial experiment is a probability experiment consisting of a fixed number of independent trials in which there are more than 2 possible outcomes for each trial. The probability of each income is fixed, and each income is classified into categories. Okay? The company wants to test a retail trade association's claim concerning the expected distribution of proportions of people who use different methods to prepare their taxes. To do so, the company could compare the distribution of proportions obtained in the multinomial experiment with the association's expected distribution. To compare these distributions, the company can perform a chi-square goodness of fit test. Okay? So a chi-square goodness of fit test is used to test whether a frequency distribution fits an expected distribution. Okay? We talked about normal, we talked about standard, all that kind of stuff. Now we're talking about a frequency distribution and an expected distribution. Fair? To begin a goodness of fit test, you must first state a null and alternative hypothesis. We're used to that. We've been doing that, haven't we? Okay? Generally, the null hypothesis states that the frequency distribution fits an expected distribution, and the alternative hypothesis states that the frequency distribution does not fit the expected distribution. For instance, here are the expected distribution, here's the claim that the expected distribution of people who use different methods to prepare their taxes. This is what the claims are. Okay, accountant would be 24%, by hand would be 20%, computer software 35%, family or friend 6%, and a tax preparation service is 15%. So to test the association's claim, the company can perform a chi-squared goodness of fit test using these null and alternative hypotheses. Okay, so we're saying the null hypothesis is the expected distribution of tax preparation methods is this, which is exactly what was in this table right here. We're saying the expected distribution is what was recorded in the table. Okay? The alternative the alternative hypothesis, however, would be that the distribution of tax preparation methods differs from the expected. It's not the expected, it differs from it. Does it all have to be different? No, it doesn't. One or two, well, probably not one, but because otherwise it wouldn't add up to 100%, right? So maybe multiple, maybe all of them are different, but there you go. Okay? To calculate the test statistic for the chi-square goodness to fit test, you can use observed frequencies and expected frequencies. To calculate the expected frequencies, you must assume the null hypothesis is true. I'm going to say that again. To calculate the expected frequencies, you must assume the null hypothesis is true. Okay? So, definitions that I need you to know. Observed frequency is we're going to use an O for observed. Okay? The observed frequency of a category is the frequency for the category observed in the sample data. Does that make sense? Okay? The expected frequency, guess we're going to use E for expected. Yes. The expected frequency of a category is the calculated frequency for that category. Expected frequencies are found by using the expected distribution and the sample size. So here is a formula that you need to know for expected frequency. For the ith category, whichever category you want, maybe the first category, maybe the seventh category, we just call it the ith. Why? I don't know. We just say ith. Okay? So you take the expected, or to find the expected frequency, you take the number of the number of trials or the sample size and multiply it by the probability of that category. Does that make sense? Okay. So finding observed and expected frequencies are pretty relatively easy, don't you think? Well, if we surveyed 300 adults and asked them how they prepare their taxes, the results are shown at the right. This is what we found, or they, I guess, because I didn't do it. This is what they found when they actually asked 300 people. Okay? So are these going to be the observed frequencies, or are they going to be the expected frequencies? Observed. Okay? There's two ways you can think about it. First of all, this is what actually happened. This is what the surveyors observed when they actually took the surveys. Also, it's down here where it says observed. That'll help too. Okay? But this is what actually happened when they took the survey. That's the results that they got. Okay? Now, to find the expected frequency, you take the percentage of people, that they told you that in this table right over here. Okay? Because that's the association's claim, is that 24% were done by an accountant. Well, if there were 300 people, and the claim is that that's 24%, that should be 72 people. Did we observe that? No, we observed 61, right? So observed is 61, expected, almost like predicted based on the numbers and the percentages that we have, that is the expected frequency. By hand, they're saying it's 20%. Of the 300, we had 42 by hand. Of the 300, they're saying 20% of those. So even though we had 42 respond that was by hand, the expected frequency would be 60 because 20% of 300 is 60. Does that make sense? And that's how they got all the rest of these for expected frequency. Took the number, which is what they, well, you can't see that. The number that they asked for, the number of trials, and it's the number of trials or the sample size, so in our case 300, and P would be the probability of that particular category. So we take the probabilities, and the probabilities come from what the insurance claim or the association claims that the distribution should be. Is that clear? Okay. That brings us to the chi-square goodness of fit test. Okay? The chi-square goodness of fit test, to even start doing the chi-square goodness of fit test, two things must be true. Number one, the observed frequencies must be obtained using a random sample. If it's not a random sample, we can't do it. Okay? The other thing is that each expected frequency must be greater than or equal to 5. Otherwise, it's going to skew our data. Okay? If these conditions are met, then the sampling distribution for the test is approximated by a chi-square distribution with k minus 1 degrees of freedom, where k is the number of categories. Okay? So in this particular test that we've been talking about this whole time about the tax preparation company, how many categories are there? 5 categories. 1, 2, 3, 4, 5. Right? 5 categories. So our degree of freedom in this particular problem would be 4, because it's the number of categories minus 1. You okay with that? So chi, oh, look what chi looks like. A fancy X. Okay? So our chi-squared test says if you take the observed frequency and subtract the expected frequency, and then square that, and then divide it by the expected frequency, and you do that for each category and then add them all up, that's the number of chi-squared. Does that make sense? Okay? Where O is the observed, E is the expected for each category. All right? Now, the cool part is that I know how to do it in the calculator. So I'll show you that in just a second. Okay, so if you have your calculator, go ahead and get it out and get ready. But before I show you that, before I show an example of how to do that, I want to make sure that we are all together to know the guidelines to actually do the chi-square goodness of fit test. Because I can show you how to do it in the calculator, but it won't make sense till we make sure we have all the guidelines down. Okay? So first of all, we have to make sure that the observed frequency were obtained from a random sample and that each expected frequency is at least 5. That was required in our goodness of fit test to begin with, so we need to make sure that that's true. Okay? Next, we need to identify the claim. From the claim, we're going to state the null hypothesis and the alternative hypothesis. Sometimes that'll be given to us, sometimes it won't. Okay? We have to figure it out. But what's going to be true about the null generally? Do you remember? Generally, the null is going to be that the frequency distribution fits the expected distribution. Remember that? So that the frequency and the expected are equal. Which means that the alternative hypothesis is going to be what? That they're not, that they're different. Okay? So then we're going to find the level of significance. Do we have to come up with the level of significance? Very rarely, right? Most of the time it's given to us in the problem, isn't it? Okay? But we need to identify that, make sure we know what we're looking for. Then we're going to identify the degree of freedom. Where do we get the degree of freedom again? Number of categories minus 1. Okay? So we're going to use that to determine the critical value. And I think that I gave everybody a new table. It is called a chi-square distribution table. Okay? We read it just like we've read the ones before. We've got degrees of freedom on the left, and we've got our percentages, or excuse me, not percentages, our levels of significance at the top. Okay? And then we just got to go match up the one that we need. Got it? Okay. So once we find our critical region, then we have to, our critical value, then we need to determine our rejection region. I know how much you guys like rejection regions. Okay? I know how much you like it so much that I found something I want to show you before we go on. I thought it was pretty funny. Now, I also think it's funny that he doesn't accept you, he just fails to reject you. So there you go. Okay? Sorry. Just little statistics humor. So once we find the critical value, that will help us determine the rejection region. All right? Use the test statistic, which I'll show you in again, like I said, and again, how to find in the calculator, and sketch the sampling distribution. There's an example of the sampling distributions on the top of the chi-square distribution to know if it's a left tail or right tail or two tails. Okay, we'll talk about that in a minute as well. And then make a decision to either reject or fail to reject the null hypothesis based on if your test statistic is in your rejection region or not. Okay, and then we need to interpret the decision based on the original claim. Okay, so let's go back to our example about the Retail Trade Association. Okay, the Retail Trade Association claims that the tax preparation methods of adults are distributed as shown in the table below. We already talked about that one, isn't it? Didn't we? And that they selected 300 people and asked them how, and we got these. What are these called? These are the observed, right? These are the categories, but these are the observed results. You remember that? The observed frequency, excuse me? These are the observed frequency, because that's what actually happened when we asked the 300 people. Okay? So, if we are using the calculator, if we're using the formula, which I just showed you on the opposite page, we are taking each of the observed and subtracting the expected, which means we have to find the expected, don't we? Okay? So, in this case, the 61% or 61 is by accountant. So the observed was 61. 61 people said they did it out of the 300, minus the 72, which was 24% of the 300. So, excuse me, we calculated that expected value. We squared that number, and then we divided by the expected value. So that one was the accountant. Then we did by hand. So 42 was the observed, minus the 60, which was the expected, which is 20% of the 300. We squared that number and divide by 60. And then we did the computer software, and then we did the family and friend, and then we did tax preparation, and then added all those together to get approximately 16.958. And like I said, you can do that. That's not a hard process at all, is it? But may I please show you how to do that in your calculator real quick? Okay. First of all, I would like you to turn your calculator on. That's an important step. Okay, let's make a new document. No, I don't want to save my old one. I'm going to zoom in real quick so you can see what I'm doing. We want to make a list and spreadsheet. Okay, list and spreadsheet. What needs to go into my list and spreadsheet are my observed frequencies and my expected frequencies. Now I have a table right here for observed and expected. Okay. So I'm going to arrow up here. I'm going to call this O, or observed frequencies. Are you okay with me just calling it O? Then what am I going to call this one? E, for expected frequencies, okay? It happens to match up with my formula that I'm going to use just in case, okay? But I could really call it whatever I wanted as long as I keep track of it, okay? So 61, 42, 112, 29, and 56. Okay, all I did was put my observed frequencies from my table into my observed frequency column. Then I'm going to put in my expected values. 72, expected frequency. I keep saying values. I apologize. 60, 105, 18, and 45. Okay, my observed frequency and expected frequency. Got it? I'm going to come over here to that spot right there. Now here's where the magic happens. It's not magic, it's just calculations, right? Okay, menu, statistics, stat tests, statistic tests, chi-squared goodness of fit, GOF. Okay, so I'm going to choose number 7. Now, where is my observed list? What did I call my observed list? O. Harrison taught me that. I can just put an O without the little bracket things, right? What did I call my expected list? E. What is my degree of freedom? How many categories do I have here? 5, so one less than that is my degree of freedom, so 4. And then it's saying, is it okay if I put the first result column in column D? It's fine with me. So I'm just going to leave it like that, and I'm going to tab down until OK is there. And I'm going to hit it. I wonder why I put it in P. Did it say P? I thought it said D. It doesn't matter. It's okay. But here's the cool part about it is, look, chi squared, 16.953. And what do they find by doing the formula? 16.953. Or 958, I can't read. 9.83. So it did all this work for us in the calculator as long as we know which buttons to push, as long as we understand what we're putting in the calculator. You okay with that? Okay. So what does that mean? Well, going by our guidelines, it talks about up here with the, up here you can't see, the hypothesis, the null hypothesis and the alternative hypothesis. Specify the level of significance that was given in the problem right there, 0.01 or 1%. Identify the degree of freedom. We already figured out that was 4. Determine the critical value. So on the chi-square table I just gave you, our degree of freedom was 4, and we're looking for 0.01. So that number is 13.277. Okay, this is a right-tailed test, so we go over here. My critical value is my critical value is 13.277. Where does 16.958 fall? Is it on the left side, or is it over on the right side in the rejection region? It's on the right side, so it's in the rejection region. If it is in the rejection region, then reject it. Okay, if it's not in the rejection region, then we fail to reject it. So we go back over here and look at what they're saying. The figure at the left, here's what this rejection region looks like. It's over here. That's what our chi-square test looks like for this problem. Okay, there's our rejection region. 13.277 is our critical value. 16.958 is in our rejection region. So we reject it, right? We reject the null hypothesis. So, do you remember what our null hypothesis was? It's that these things that they said were the claims. Okay? Well, there is enough evidence at the 1% level of significance to reject the claim that the distribution and the observed distribution and the expected distribution are the same. Okay? We reject that claim that they're the same. Does that make sense? Okay. So there's several other examples in here talking about M&Ms. I love examples that talk about M&Ms because I just like M&Ms. Okay. But that's all of section 10.1. Okay. So the important section in 10.1 is the chi-square goodness of fit test and the guidelines for running a chi-square goodness of fit test. Okay. Any questions about that?